Welcome to Graphing Square Roots and Cubic Functions. So we're really just going to focus on how do transformations actually affect the domain and range of these graphs. So we've already seen transformations and these functions, but I just want to do a quick refresh. So go ahead and take a look and try to graph the function f of x equals the square root of x. Well, I could try to plug in some numbers to see what it would look like. Well, if I try to plug in -4, we saw what happened with that. Those are the ones where we got imaginary numbers. So I can't do square root of negative numbers, but I can plug in and get the square root, and I would get, square root of 0 is 0. Well, that's a really, really friendly coordinate. I can continue on. I can try to plug in 1, and okay, square root of 1 is 1. That's really friendly. If I try to plug in square root of 2, I don't know what the square root of 2 is, but I do know the square root of 4, and that's the same thing as 2. So I'm putting in the number 4, and I'm getting out the number 2, which also happens to be our square root parent function. It's what it will start looking like before we start moving it around. Okay, domain. What can I put in a function? Left to right. Well, we can see I can't put negative numbers in. We can even see that in the graph. There's no parts of the graph that are over here. Looks like I could plug in 0. I can plug in every number after that. So I can bracket 0 to infinity. Range, bottom to top. Well, I can see that I plugged in and I didn't get any negative y values. I really just got positive y values and I got 0. So it looks like the range almost matches the domain. Bracket 0 towards infinity. Here we can see with g of x, I've got some transformations. I see a 4 underneath. I see a +2 on the outside. So +2 on the y values will shift the graph up. 4 underneath is going to shift the graph to the right by 4. So for that, if you're curious, here were your transformations, and here was your domain and range for that graph. So I'm going to go ahead and sketch it on here so you can also see it. Here's this orange graph. I'm going to label that g of x. And you can see how the domain is now at 4, and the range bottom to top is 2 to infinity. But I can also see how the domain and range affected that. I shifted right 4, so the domain is 4 to infinity. I shifted it up 2, so the range is now 2 to infinity. All right, h of x was probably the trickiest of the three because there were actually lots of transformations to take a look at. I have an exterior, I have a 2, and I have a -3. So there's really nothing on the inside with x. So it's really after I square root that I have all these changes like this one. I'm going to subtract 3. So that's going to shift everything down by 3. I'm going to flip everything and make them negative. So all my y values are now negative. And I'm going to double everything. I see a 2. It's getting multiplied on the outside. So all three transformations, a flip on the x-axis, exterior x-axis, vertical stretch by 2 because it's doubling all those y values and shifting down by 3. So domain, I didn't shift left and right, so that's still at 0. But the range looks a little different. So let's check out a sketch to see why the range has changed so much. So here I'm going to go down 3. I'm not shifting left or right. Okay, let's see what happens when I try to stretch. If you're unsure what the stretch will look like, try plugging in a number. So here's my function, -3. I'm going to try plugging in the number 1 because square root of 1 is super friendly. All right, so I've got -2 -3 is -5. So 1, -5 is going to be on that graph. And I can see, down 2 over 1. So you can kind of see the stretch there as well. And that's going to be h of x. So be sure you go ahead and label that. All right, and I can see, okay, there's all my transformations, and there's where the range is. Bottom, so -infinity up to -3. But we can also see that flip caused the y values and the down 3. So all of those changes happen to be there. All right, here we're going to try to create a square root function where the domain is -4 to infinity. So I always like to leave a bunch of notes to myself like, okay, these are my x values. I'm looking for ones that are bigger or equal to -4. Okay, the range has to be below -infinity up to 7. So those are all my y values below 7. So now I'm going to try and do a quick sketch. All right, domain looks like it needs to be -4 to infinity. So I'm going to shift it this way. Well, I can already tell I'm going to have to shift the graph left 4. So that's definitely something to keep in mind. And then it says I have to be below 7. Well, now I'm going to have to figure out what that's going to look like. If I try to just shift the graph up 7, well, that's not 7 and below, that's 7 and above. So what would happen if I went ahead and flipped this graph instead? So now I still have -4 to infinity, and now I have everything below 7. So I'm going to have to write all those down. I did a flip on the x-axis, so I flipped everything upside down. And then I also shifted it up 7. So for your final answer, I'm going to have a flip on the exterior, and then I'm going to have to shift it to the left by 4. Normally, we always see these extra minus signs. So I'm going to shift it kind of -4 because I shifted it over here. And then I'm going up by 7. So just be sure for your final answer, I'm going to use purple so it matches my pretty sketch. Negative on the outside, I see a +4, and I see a +7. All right, example 3, I've highlighted some key words. So I've got the x-intercept is at 0, 0. Without using transformations, how could we find the x-intercept of this function, g of x? Well, x-intercepts are where the graph crosses the x-axis. So x has the number, y is equal to 0. So maybe we try to solve for it instead of trying to think of transformations. So I'm going to look for my x value, -8, and see if I can find it this way. Well, I see a square root, so I'm just going to go ahead and square both sides to undo it. 0 times 0 is going to give me 0. And then I just have x -8 left over. So it looks like at x is equal to 8, that's where I would have an x-intercept. So here is actually what it's going to look like. And now you can see why the graph actually moved right 8 and not left. That's why I like this question. It really helps you see why is the graph shifting right, even though I see a -8. All right, on example 4, I've got 2 transformations. I see a -3 underneath, and I see a up 4 +4. So we're going to shift the graph to the right by 3, move it up 4. So hopefully here is what your k of x function is going to look like. You'll see I have the original parent function kind of in gray, and you can see where I've shifted it right 3 and up 4. So the red graph is where I'm focused on. All right, domain, again, is going to be left to right. What x values can I put into this function, and what would I get? Well, I can bracket 3 to infinity. And again, I can kind of see that I went right 3, so the domain got affected. Lowest value is 4, and then it's going up, 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 up. So bracket 4 to infinity. This next part is kind of using a conjecture or making a guess. So here I can see that here's k of x, which is this piece, wants to know where that is equal to 0. So here's the thing. If I try to look where this function actually is equal to 0, well, that would be right here. Odd. The graph never actually gets to this line. It's always above that line. So if I tried to actually solve this, I should get no solution because that function never is going to equal 0. It's not an option. All right, we're going to switch gears and take a look at some cubic functions. This one in particularly is the cube root function. So again, you can always try to plug in some points like 0. Cube root of 0, okay, that's 0. You can also try plugging in the cube root of 1 and get 1. You can even plug in the cube root of things like -8 and get -2. And it works out really, really nicely. So here's what your cube root function is going to look like. Domain and range work out really nicely because it looks like I've got all the negative x's. I've got all the positive x's. So I've got -infinity to infinity. Range bottom to top, also the same thing. I have all these negative y values. I'm going to keep going, and I'm going to have all these positive y values. You've got some transformations here. So I'm going to go left 4 and I'm going to go down 5. You can see how I rewrote mine in orange to help me see it. So again, I'm going to go left 4. I'm going to go down 5, no stretching, no compressing, and no flips. So I kind of get to move all of these points. There we go. Good enough. And this is going to be g of x. Again, domain and range are going to be friendly because I have all the negative x's, all the positives, and same thing with the y. So nothing is getting restricted. I can still plug in negative numbers and it works out okay. All right, h of x is going to be a little different. Hopefully you saw 1, 2, and 3 transformations. But on this one, you'll see that the x is all by itself. So hopefully you didn't shift the graph left or right at all. We just had a couple things happening on the y values. We had a flip on the x-axis, a vertical stretch. Everything was getting multiplied by 3, and we shifted everything up 3. But again, I like cube roots because their domain and range is still all real numbers. So transformations don't really affect these that much. So I get to stretch 1, 2, 3. And I get to stretch 1, 2, 3. So it's going to be this huge stretch in the graph, almost kind of like that. It's not the best picture, but again, we're just going to do some sketches. You can always try to plug in for a coordinate. So I've got -3, cube root of 1 plus 3. Oh, -3 plus 3. Yes, gives me 0. So 1, 0 is a coordinate on the graph. Not too bad. Still all real numbers for domain and range. Man, I love a good cube root function. So in this one, hopefully you shifted the graph left 2 and up 1. D of x, you had 3 transformations. You had a flip on the x-axis. You should have shifted that one right 2 and down 1. And then finally, f of x, we should have had right 1 and down 2. So hopefully that gave us these 3 different graphs. So we got left. There we are, all 3. And again, these are just sketches. They're not going to be perfect, but the idea is there. Now it says go ahead and write one observation you have about the relationships between these functions or between 2 of them, because I'm going to draw myself a nice pretty line because I'm starting to see it looks like there's 2 functions that have been flipped over, that f of x and b of x. Well, let me go ahead and take a closer look. Right here, I've got a coordinate at 3, 6, and here I have a coordinate that's at 6, 3. I know we've seen functions like that. You have, these are inverse functions, and that's one of the coordinates you can kind of see where they work. So again, inverse functions are reflected across this y equals x line. They're the ones where we switch domain and range, and you can kind of see how that happens right here. Your x's and y's have swapped. And we're going to review how to find these algebraically, but I wanted you to see what it looked like visually as well as a good reminder. Here we're going to take a quick look at an application of square roots. Why are these actually helpful? Why are they actually needed? If you are in our lovely photography magnet, you probably can see how these are actually related. So if I'm standing 1 meter away, the amount of light that I'm actually going to have is at 100%, or the quality of light that I'll actually have is at 100%. So 1 meter away at 100%. Here's what's interesting. If I stand 2 meters away, I'm actually down to 25%. If I stand 4 away, I'm down to 6.25, and if I'm at 3. Now, these relationships are definitely a little bit interesting because it looks like I'm at 2, and then I can see light quantity is 1 over 4, 3, 1 over 9, 4, 1 over 16. It's starting to look like a pattern here. This pattern is actually called the inverse square law, and it's actually how light and distance work together. This is just one application in photography. So I can kind of see what happened where I would plug in, let's say, a distance of 2. I squared that distance, and then it looks like I did the inverse of that because it says the power of light is inversely proportional. So that's a very fancy word. But all we did was just take the distance and square it. And then we found the inverse, or we flipped it. And that told us how much light we actually would need. So here's where square roots are actually helpful. So now we're actually going to try to solve what we just did up here for the distance. So I'm just going to do a little bit of working backwards. So I'm going to go ahead and multiply both sides. So I'm going to have d squared times light is equal to a 1. All right, and then I'm going to go ahead and divide by the light. So I'm going to have distance squared is 1 divided by the light. Oh, and there's where square roots are coming to the rescue. So the distance is the same as the square root of 1 divided by the amount or the power of light.